Hello everyone, welcome to my talk. I'm Haonan Li from Southern University of Science and Technology. This work is collaborated with Wei Jie, Mingde, Hongyi, Zhenyu, Heming, and Fengwei. So today I will introduce our work, Ashman, a novel memory management for RISC-V enclaves. Recent TEs on RISC-V usually meet two limitations. First, their concrete enclave numbers is usually restricted. Second, some features like memory request is still limited. These limitations are usually brought by their memory protection mechanism. Let's take the physical memory protection or PMP as example. The PMP is a standard hardware component for RISC-V, so lots of TEs rely on PMP to protect their enclave memory. The PMP can configure like accessibilities for contiguous memory regions when CPU turns on to the host OS. Suppose there are n enclaves, it will need like n+1 PMP entries to configure this amount of memory regions for each enclave to protect each enclave. And for when one CPU turns to the enclave, say enclave 1, it only needs like one PMP entry to cover the enclave memory. So the PMP is really powerful and handy, but it has a limited number of entries. From RISC-V standard, it can only support at most 16 entries. Therefore, here comes the first limitation. The number of enclaves is actually limited by the number of PMP entries. To overcome this limitation, a straightforward way is using one PMP entry to cover the whole enclaves like this. This way, no matter how many enclaves there is, we always require only one PMP entry to protect all enclaves. The shortage may be the useless sandwiches. We call these sandwiches the memory between enclaves. It cannot be used by host OS, and it can only used for enclaves in the future. So, but we think comparing to the larger amount of the whole memory, this memory of RISC is acceptable. The second limitation is a bit more complicated. If enclave 1 needs want to use more memory, say just something like it will need an extra 4 blocks in their runtime. So due to the limitation of PMP, the new memory region can be only located to its adjacent areas. So this means the request of memory requests result of the request and not always keep the same. For example, in this case, all things goes well. You can directly put these 4 blocks to the adjacent area and the request will succeed. But if in another case, you will see the enclave 2 use a bit more memory than before. So in this case, this sandwich area is not enough for 4 blocks. It can only allocate like 3 blocks. So you will see that this is the limitation, that the memory request depends on other usage. The enclave 2 use more memory, but it affects enclave 1 cannot finish the request. It's not really wired. And here is the limitation 2. The memory request is limited. To solve this challenge, we introduce memory migration. It means to move memory to another location. Continue to our last example. In this example, we can firstly allocate like 3 blocks instead of 4. But with the help of memory migration, we can like migrate the next enclave 2's memory to another side, like this, and to make room for the last one. So you will see we can finish the memory allocation. And let's talk about the time complexity of the allocation algorithm based on the migration. So let's consider the worst case. Suppose there are n enclaves and it requires like m blocks, and all enclaves are aligned closely. So in this case, if enclave 1 still needs 4 blocks, it will need like 4 times 2 migration, like this. Okay, 4, 8 migrations. So it will cost a relatively very high big overhead. It's not acceptable. To reduce the overhead, Ashman allows fragmentation. It means we allow enclave to have multiple fragments. Let's recall how we use PMP to protect memory. Note if that the CPU runs on the enclave 1, we only need one single PMP to restrict the enclave 1 to be only used if on memory. So in this case, we can make full use of PMP entries and directly put the requirement to another sufficient free space. So we use an extra PMP entry to finish the memory request very directly. Allow fragmentations and make full use of PMP entries. Still, there is another situation. Because the PMP entries is still limited as we mentioned before, when the PMP entries runs out, we introduce the smallest fragment migration. It means we will firstly find the smallest fragment of enclave 1 and move 1 to another free space and to finish migration. There is when PMP entries run out, we can migrate the smallest fragment to another free space to finish the allocation. Still, there is it a final case? You will see, in this case, the largest free space has only 3 blocks, and its smallest fragment is only 2, has 2 blocks and only 3. So you cannot just migrate, make no sense. So in this case, we introduce the memory compaction. It means we will scan each blocks being allocated, memory blocks to be allocated, and move it to the left as possible. So in this way, we can like make the largest free space on the other side, on the right side. So if, but you will see, although we do make the largest free space, we cannot simply put these 4 blocks to this area because it will introduce another fragment. We have said we have only 3 fragments to be used. And so maybe an ultimate solution is to performing the compaction along with like merging fragmentations. It is also one of our future work. So now let's recall the whole procedure of the memory request. First, we will check if there is an adjacent memory space. If true, then we directly expand previous one to finish the allocation. Otherwise, we will estimate if there's free PMP entries, allocate it to a new fragment or perform migration. And finally, considering the compaction. We evaluate Ashman from 2 aspects, memory utilization and performance. For the memory utilization, it is measured by the ratio of the used to be the total memory or the used to the memory pool. We evaluate Ashman in different sizes of memory pool for different numbers of enclaves, and the result shows that in any Ashman can improve by like 1.5 times to 5 times. A huge improvement. These figures use the performance of memory allocation. Due to the lack of optimization, Ashman is much slower than Linux allocation algorithm. But you will see the time is relatively small because you see for 32 megabytes, it requires like smaller than uh, 10 power of 8 cycles. So it is relatively small for the whole execution time. And the trend you see is linear. So the bigger the overhead is reasonable. And the turning point is 8 megabytes. It is also the size of our the smallest unit for allocation and migration. As for the memory migration, its overhead is basically proportional to the size to be migrated. And as for the compaction, the time of compaction varies for memory pool and the migrated partitions. Typically, in our experimental memory pool with like 768 megabytes, it will take like about 10 seconds to perform a compaction. So we should reduce the number of compaction as possible. So in conclusion, we propose a solution for memory allocation enclaves to overcome the limitations due to current memory protection mechanism like PMP. So with Ashman's help, we believe the enclave application can use memory as native applications. And besides, we only relies on RISC-V standard hardware, and the overhead is relatively low. We also open source our code to help further research at here.